Welcome to DBA 110, Lesson 2, Secure Table Design and Data Entry Validation. In this lesson, we're going to focus on protecting sensitive information through proper table design. By the end of this lesson, you'll have the knowledge to build tables that are not just functional, but also secure. Let's get started. In this lesson, we'll learn how to define fields and assign appropriate data types. We'll review validation rules. We'll talk about how validation helps reduce cybersecurity risk. We'll look at how poor table design can be exploited through attacks like SQL injection. We'll explore the role of secure database design in maintaining the CIA triad: confidentiality, integrity, and availability. We'll look at validation features and how they connect us to real-world cybersecurity practices. Before we dive in, take a moment to think about your current knowledge of secure table design. Have you used data types and validation rules to prevent security threats in a database before? This self-check helps you determine a baseline for your learning today. By the end of the lesson, you'll be able to explain how table design can protect your data from threats. Let's define secure table design. At its core, secure table design means building your tables in a way that prevents errors, misuse, and security threats. This starts with structuring your tables properly, choosing the correct data type so that only valid data is accepted. It means using validation rules like required fields, ranges, and input masks to ensure that data is accurate and meaningful. It also involves enforcing required fields so that critical information can't be left blank, preventing data corruption and attacks by blocking incorrect and malicious input that could damage your database or leak sensitive information. Secure table design is all about ensuring that only clean, correct, and safe data can be entered. This keeps your database trustworthy and protected. Why does secure table design matter? Because it keeps your data accurate, reliable, and safe from harm. Without proper design, databases are vulnerable to human error, accidental loss, and even cyber attacks like SQL injections. Invalid or missing data can lead to poor decision making, system failures, and even data breaches. For example, storing critical data without validation can let in malicious inputs and cause calculations to fail. By designing tables properly and validating data, we can protect sensitive information, ensure accuracy, and build trust in any system that depends on that data. Let's talk about why data types are so important. Imagine you save a phone number as a number field instead of a text field. That would be a problem because phone numbers actually include hyphens, and the database would actually strip those out, leaving you with incorrect values or even worse. Fields define what type of data a table will hold, and choosing the correct data type prevents errors, confusion, and data loss. This might seem like a small thing, but choosing the wrong data type is the most common mistake in database design, and it can have big consequences. Consider this question. Have you ever filled out a form and noticed that your zip code changed or your phone number looked wrong? Important things to consider about setting up your table. In field design in a database, this allows you to choose the correct data type, give the field a proper name, and set other properties like field size, format, and validation rules. If these things are not done correctly at the start of the creation of the field, then you run the risk of losing important data. You run the risk of numbers performing wrong calculations, misleading users, and serious reporting issues and possible security threats. A field name is a single category of data in a table. For example, first name, birth date, total due. When you set up the structure of your table, the first thing that you do is give the field a name, and then you are able to select a data type. The data type represents what type of data you plan to store in that field. Some examples of common data types include short text, number, currency, date, time, or yes, no. In Design View, you will define the table structure before entering any data. You will give each field a name and select a data type. You will also set properties like required, default values, validation rules, and field sizes. This is where you lay the blueprint for your table and define the structure. In Datasheet View, you can enter, edit, and view data in rows and columns, similar to a spreadsheet. You can also add fields in Datasheet View, but the design choices that you make in Design View actually guide and control what you are able to enter. Both views are important, but Design View is where you secure your data. Datasheet View is where you enter the actual data. Now let's look at some common mistakes in field design that can cause big problems. Dropping leading zeros. If you set a zip code field as a number, values like 02115 will become 2115. Because if that field is set as a number, then it is going to drop the zero, the leading zero, and that will misrepresent your data. So how do you fix that? Instead of making zip code a number data type, you should use short text. So that way those numbers are treated like text and it will not drop any leading zeros. Another example is incorrect calculations. If you store the GPA or someone's age as text instead of number, you can't calculate anything about those numbers or sort them properly. Always make sure that you use the correct data type to ensure that you have accurate precision. Another example are phone numbers. Storing a phone number as a number. When you do that, you are going to lose formatting like the parentheses around the zip code or dashes between some of the digits may disappear. Instead, use short text, possibly with an input mask as needed. Storing a phone number as text will retain parentheses and dashes, preserving the format of a number. Another example is mixing data types. Storing both dates and text in the same field can lead to errors when you are trying to sort and analyze data. Always use one data type per field and separate data categories into their own fields. These design mistakes just don't cause errors. They can also introduce security vulnerabilities. Data validation is your first line of defense against bad data and cyber threats. For example, what happens if someone types text into a field that expects a number? Or if someone types 300 as an age? Well, we know that's clearly out of range. Input validation sets rules for what's allowed. It protects your data from accidents and blocking many simple cyber attacks. Validation keeps your database clean, safe, and reliable. When thinking about validating data that is going to be input into your database, we want to keep in mind a couple of things that we're looking to prevent. Data corruption. We want to stop incorrect data from being entered into the database because it can ruin calculations. If someone is allowed to enter bad data and someone later tries to use that bad data to analyze something, it can cause confusion and can result in data loss. System failure. Entering data in the wrong format can actually crash the system or freeze a form. It can spread errors through different reports, charts, and other user forms. If you are not taking precautions to validate data before it's accepted into the database, hackers can often exploit weak input validation. A hacker can enter code or unexpected values into your input fields. And if you're not validating that for security purposes, it's allowed to enter your database. Here's an example. A hacker might type something like drop table students into a text field. Well, if your database is not set up to block that type of code, then it has the potential to delete a whole table from your database. This is called SQL injection attack. And it works when a system does not check or block invalid input. If you allow a user to just enter anything and your database accepts it, you run the risk of being a victim of an SQL injection attack. Let's discuss 3 types of validation rules that can help protect your database. Range validation. This sets up the database to only accept values within a defined range. For example, you may say the age must be between 13 and 120. It's not going to accept any value that's outside of that range validation. Legal values accept only specific pre-approved entries. Like the grade level must be grade 9, 10, 11, or 12. It's not going to accept any other grade level. Input mask. You can force a specific format, like a phone number can have parentheses around the area code and a dash between certain digits. These validation rules help prevent accidental errors, like typos and wrong formats. It can also block malicious input that could damage your database, or let in code that doesn't belong, like an SQL injection. Imagine someone enters code instead of a name in a form, and that code deletes your entire student records table. Does that sound extreme? Probably so, but it happens all the time. This is called an SQL injection attack, and it can destroy your data. That's why input validation is so critical. It prevents the system from executing unexpected code and protects your database from being compromised. An SQL injection is a type of cyber attack where a malicious user inserts or injects harmful SQL code into a database through a vulnerable input field, like a login form or search box. Most web applications and databases use SQL to manage data. When an input field, like a username, doesn't validate or sanitize what a user types, a hacker has the opportunity to enter code instead of regular data. Let's break down an example of an SQL injection attack using something you might see in a login form. Imagine you have a typical login screen where the user enters their username and password. So behind the scenes, the system runs an SQL query like the one you see here, where user equals input and password might equal input. A hacker wants to get around the login without knowing a valid password. So instead of entering the normal username, the The hacker might type or 1 equals 1. When that is entered into the system, it's going to change the SQL code that the form expects, because 1 equals 1 is always going to be true, no matter what. Because 1 equals 1 is always true, the query is going to trick the database into thinking the condition was met, even though the attacker didn't supply a valid username or password. The hacker is going to be able to get into this system and bypass the login screen entirely. This is a classic example of an SQL injection, where the attacker exploits poor input validation to execute a harmful query. With SQL injection, hackers can do a lot of damage. They can view sensitive data. They can bypass login screens by tricking the system into logging them in without a password. They can delete or change data, drop an entire table, or alter account balances. They can even install backdoors for future access. So how do we prevent SQL injections? By using input validation. Only allow the correct type of data to be input into the database. We can sanitize inputs, strip out harmful characters like semicolons and single quotes before sending data to the database. We can use parameter queries and stored procedures. These will separate user input from SQL logic, so the system knows what's data and what's a command. We can limit user permissions. Give users only the access they need, no more. Viewing sensitive data means that a hacker can write SQL code that tricks the database into showing data it's supposed to protect. An example would be a hacker enters malicious input into a search field that modifies the query and returns all user records instead of just one. This would be a violation of privacy laws like HIPAA and FERPA that can result in data leaks, identity theft, or regulatory fines. Bypass login screens. This means that an attacker can use SQL code to trick the system into logging them in without a password, giving them unauthorized access, just like we saw in the previous example with the SQL injection attack example. Why does this matter? This gives hackers admin level access to systems that they shouldn't be able to enter, potentially exposing the entire database. SQL injections can be used to alter or delete data in a database. An example would be a malicious query could change all account balances to 0 or remove user records. This compromises the data integrity, making reports inaccurate, disrupting operations, and erasing critical records. An SQL injection attack can include commands like drop table. This would permanently delete entire tables from your database. This can result in catastrophic data loss, can shut down systems, and require costly recovery efforts and damage the trust. Attackers can also use SQL injection to insert database code in a way that allows them to return later, even after being discovered. Injecting commands to create new admin accounts to silently log in usernames and passwords. Backdoors allow ongoing hidden access, making systems very vulnerable even after the original breach is detected. We can use tools like input validation to prevent SQL injections. This means that you're going to check and restrict what a user can enter into any input field. Input validation ensures that the data is of the right type and within expected limits. Why does this matter? If you only allow valid data, you reduce the risk of someone slipping in harmful code. Remember, this is your first line of defense. We can also sanitize inputs. This means that we can clean the user input by removing or neutralizing harmful characters, not allowing single quotation marks or semicolons or SQL words before sending it to the database. Sanitizing input helps ensure the database interprets the input as data and not a specific command. Parameterized queries are a way of writing database queries that separate the SQL logic from the data inputs so that the user input is treated as data, not as part of the SQL command. This will help prevent SQL injection attacks because they treat the user input as a value to be plugged into the query rather than something that might change the structure of the query itself. This prevents attackers from injecting commands since the system knows exactly what parts of the query are logic versus user input. We can also limit user permissions. You can configure your database account so that front-end users, like people who are going to interact with your database, only have permission to read or insert data, not delete or modify database structures. Even if an attacker gets through, they can only do certain things, and that's going to limit the damage that they can cause because they have restricted access. Secure database design plays a foundational role in maintaining confidentiality, integrity, and availability of information. This is the CIA triad. It represents strong design equaling strong defense. Confidentiality. The goal is to ensure that sensitive data is only accessible to authorized users. This can be done through access controls, data classification, encryption, and authentication mechanisms. An example of ensuring confidentiality: only HR staff can access employee salary records. Others are restricted. Integrity. The goal of integrity is to ensure that data is accurate, consistent, protected from unauthorized modification. We can do that through the use of validation rules, referential integrity, audit trails, and input sanitation. An example of ensuring integrity includes a student's grade cannot be changed by a user who does not have permission. All changes in the database are tracked. Availability. The goal of availability is to ensure that data is accessible to authorized users when they need it. Some examples of how we can support this include backups and recovery plans, optimized design, and access management. An example of ensuring availability includes a properly indexed student registration database that remains responsive during peak enrollment times. That means that the system is readily available when it's needed. Let's consider this case study. This is involving TSA Flycast SQL injection. In 2024, security researchers discovered a serious flaw in a system called Flycast, used by some U.S. airlines and the TSA to manage access for pilots and the crew. This flaw was an SQL injection vulnerability. This essentially means that the system did not properly check data that was entered into the system. This allowed researchers to trick the database and gain full administrative access. Someone was able to create fictitious crew members, enable individuals to bypass security screenings, and gain access to the aircraft. Researchers reported this vulnerability to the Department of Homeland Security and the TSA. Once it was reported, the disclosures were initially ignored, and they attempted to downplay the severity of the findings. And they claimed that that's not the only method of verification that we use to board a flight. So what are the lessons learned here? We can't underscore the critical importance of proper input validation and implementing secure coding practices to prevent SQL injection vulnerabilities. This could have had a severe implication on our national security and public safety. Congratulations! You've completed this lesson on secure table design and data entry validation. Reflect for a moment. How confident do you feel now about using secure table design to prevent security threats? Remember, secure design isn't just about keeping data accurate. It's about protecting it from misuse and attacks.